Okay, well, good afternoon, good morning, or good evening to everybody. This is the fifth of our webinars in the current sequence of 6 webinars delivered by Ristec. Welcome to this webinar on fire and gas detection policies. Yet again, it's great to see so many people interested in this important topic. For those of you who haven't met me before, I'm Vicky Billingham and I look after Ristec's training and education business. Just before we go any further, a little bit of housekeeping. I'm going to mute everybody. I've muted most of you already, simply so that everyone can hear the presentation the best way possible. If you'd like to ask questions, then please leave those to near the end, but if you'd like to type them into the chat function, I will make a note of them and then we'll go through some of those questions at the end. I'm afraid we won't get to answer every question because there are so many of you attending, but we'll do our best. I'd now like to hand over to John Wiseman, who is a consultant with Ristec with extensive experience of the oil and gas and nuclear industries, and he's going to take us through the presentation. So over to you, John.
Okay, thank you, Vicky. So, as Vicky said, my name is Jonathan Wiseman, and firstly I'd just like to thank everyone for taking the time to listen in on this webinar today. I really hope you find it interesting and well worth your time. So just as a brief introduction to Ristec, and I won't go into too much detail on this, many of you will have come across Ristec in the past. We are a specialist risk and safety management consultancy, and we aim to support our customers in these 5 main areas. And so if there are any particular aspects of these services that you would like to find out more about, then please do get in touch. Okay, so for this webinar, I'm going to be talking about the main considerations that need to go into the development of a fire and gas detection philosophy. So I'm not going to cover the detailed requirements of these documents or the exact contents, but I'm going to cover the main elements and the approach that should be taken to development of a fire and gas detection philosophy. So, as we know, during the design stage of projects, many philosophy or design basis type documents are developed at the project start, and these are primarily developed to assist the project in decision making as it progresses more and more into detailed design. However, of these sort of philosophy type documents, the fire and gas detection philosophy document seems to be one of the more well debated documents. So in these first slides, I'm just going to present a number of reasons as to why fire and gas detection design can be a challenge. So the first reason is primarily due to the lack of guidance. So whilst public guidance does exist for the development of fire and gas detection systems, these are primarily aimed at detection for indoor locations, and this is probably because it is much easier to follow a prescriptive regime for detector placement indoors, where the hazard is contained within the walls and the ceiling, and it makes it much easier to place detectors when we know where the hazard is going to be, and it is much more predictable. However, for loss of containment scenarios outdoors and fire and gas detection outdoors, there is distinct lack of guidance to engineers on how to design the fire and gas detection system, and what is actually available is very much open to interpretation. Another reason why it is a challenge is that there are basically so many choices to the designer. There are so many solutions for the fire and gas detection system, with manufacturers each having their own individual data sheets for different technologies, for the different detectors, and these individual documents, whilst very useful for specific components, shed very little light on how they must be integrated into the overall detection solution. And finally, the main reason why guidance perhaps is not as prescriptive for fire and gas detection in process areas, in outdoor areas, is because of the variability of the outcome. So here I've listed a few variables that may be considered for potential releases across a facility. So we have the leak location, and obviously the bigger the facility, the more potential locations there are. There's the release direction, there's the size of the release, there are the external influences such as the wind speed and the wind direction, and then of course there is also the ignition sources to consider. If it ignites, we then have the fire hazard that must be detected. So if you multiply all of these factors together, what you actually end up with is pretty much an unimaginable number of scenarios for which our fire and gas detection system must be designed against. Other reasons might be the type of facility. So for example, onshore facilities have much more space, and therefore we have much more freedom for our evacuation routes. We can separate our places of safety much further away from the process equipment, and because of this we might choose to take a bit more time on what action to take prior to shutting down the facility. Whereas offshore, obviously much less space, much more congested environment, people are typically working in and amongst the equipment, and we have there is a much more significant risk of explosion. So for an offshore facility, we typically require a much more fast-acting response on fire and gas detection. And then finally, there are the different types of hazards that we must detect once the loss of containment has occurred. So we have the flammable gas hazard and the resultant explosions that may arise from this. And then there is also potentially toxic hazards and the direct threat this poses to personnel. And then of course, as I've said, if the release is flammable and it ignites, we have the fire hazard arising from that. So clearly there's no one size fits all solution for the fire and gas detection system. And in fact, it must be accepted really that not every release can be detected. In fact, a review of the hydrocarbon release database for between 2001 and 2008 indicates that 69% of significant releases actually go undetected. So clearly there is much room for improvement here, and I think that this starts with development of a robust fire and gas detection philosophy that sets out the main objectives and the requirements of these systems. So before we go on to define the actual objectives or the general objectives of a fire and gas detection system, I think it's important to first understand the limitations of the role it actually plays in risk mitigation. So the first thing to understand is that the fire and gas detection system, or the fire and gas detection in its own right, does not actually reduce risks. So as illustrated by this diagram on the right, the detectors must also interface with the subsequent steps. So here it must also interface with the decision logic, and then also the resultant action that comes out of the detection. And one further point to note actually as well is that the fire and gas detection system only serves to mitigate. It's only part of the consequence mitigation system, and therefore it might actually be more beneficial for our risk reduction efforts to be prioritised more towards preventative measures, such as more frequent maintenance and inspection, or better process monitoring and control systems. As we know, effort spent on sort of these prevention measures has a much more direct correlation with risk reduction, and it may be that we've reduced the risks to a sufficient level such that there is an argument that fire and gas detection is not required at all, actually. So once we've decided or come to the conclusion that fire and gas detection is needed for our facility, what are the main general objectives that we place on these systems? So obviously, it goes without saying, the system must detect, but it must detect and provide early indication, early detection to minimise consequences and prevent escalation. It must also go on then to alert operators, either the operators in a control room or field personnel located throughout the facility so that it can go on to take timely action and evacuate the area. And this alert step must also provide sufficient information to the operator so they can take appropriate action. So it may be information in regards to the size of the hazard, the size of the fire, the size of the gas cloud, and the location of the hazard. And then finally, with this information, action must be initiated, and this action is the end element that actually serves to reduce the risks. So this action may be automatic if we want a quick response, or it may be manual from an operator at a control room, for example, who makes a decision on the given information. Resultant actions may be things such as isolation and blowdown, electrical isolation if we want to minimise the potential for ignition of gas clouds, initiation of any active fire protection, for example deluge systems over vessels, for example, and closure of dampers if we have detected, for example, gas in a ventilation system. So these are generic objectives, and obviously they must be tailored for different facilities or a specific project in hand. Okay, so now we understand the limitations and key objectives of the fire and gas detection system. One of the key stages we must go through in development of a philosophy document. So understandably, there is a critical link between the requirements on the fire and gas detection system and the hazard and risk assessment. In order to understand the requirements for fire and gas detection, we must first also understand the level of risk posed by any sort of loss of containment scenario. And we must therefore appreciate the risks to assets, to personnel, and of course any environmental risks. Understanding these risks enables us to extend our general objectives to more specific detailed requirements that serve to reduce the risks for that facility or for a particular area of the facility. And once we have defined the risks, we can then go on to once we have defined the requirements coming out of our hazard assessment, we can then go on to choose the right technology that satisfies the requirements and is suitable for the hazard that is actually being detected. Very much in tandem with choosing the right technology, we must decide on a detector layout strategy that satisfies the requirements, and then coming out of this, propose our detector positions. Once we have our detector design or preliminary design, we can then go on to assess its performance to demonstrate that the requirements are being satisfied. Now, this performance assessment may reveal that the actual requirements placed on the system are not being achieved, in which case we have to go back perhaps to choosing more appropriate technology or redefining our detector layout. Finally, once the system has been designed and it's going through commissioning and operations, we must undergo continuous review of the system. And then, of course, from this review, it may be hazards may have changed throughout the operations, in which case we're back to step one, where we have to review the hazards and perhaps redefine our requirements on the system. Okay, so I'm going to go through each of these stages in a bit more detail now. So, as a risk mitigation system, the fire and gas detection system should have very close links to the risk assessment. So as we know, there are a wide range of techniques for assessing facility hazards, from qualitative techniques using hazard or checklist type approaches to fully quantitative methods that may use analysis techniques such as computational fluid dynamics. One effective method to visualize the potential fault scenarios is through the use of an event tree, as shown here. So these are, as we know, these are primarily used as a quantitative assessment tool. However, they can also be used to illustrate the various outcomes that may arise from a loss of containment scenario. And if we choose to apply numbers to the event tree, so frequencies and probabilities, what we end up with is we can determine the highest risk contributors of these different outcomes, and we can therefore design our detection system against the highest risk contributors. One equally valid approach to that could be just a checklist type approach, where we basically run through the properties, the process material properties, so its pressure, its temperature, its flammability and toxicity. The nature of the release, is it high, will it form a high pressure jet? Is it a dense gas? Is it more buoyant, and will it go upwards, in which case our detectors must be placed at a higher elevation typically? Or is it a liquid release which could then go on to form a vaporizing pool? We may also, in addition to the nature of the release, we need to consider the potential consequences of the leak in view of its environment, so the congestion levels and the explosion risks that higher congestion levels give rise to. Is there any vulnerable assets, or large hydrocarbon inventories, for example, or of course any personnel? The topography of the sites may also be considered in this checklist. So, for example, are there any sort of sumps in which gas may sink into? We may also consider the dominant wind direction, and then review any ignition sources that may give rise to a fire hazard. So this could be done in the philosophy document, but for many projects in the oil and gas industry, we also perform other studies such as quantitative risk assessment and computational fluid dynamics. If these studies are available, then these can be used to gain more insights into the nature of the hazards. So once we understand our hazards and we have we've decided for which particular hazards we are going to design the system against, we are then in a position to define the requirements. So I've listed here a number of requirements. This is by no means comprehensive. So response time may be determined by the speed with which consequences could escalate further. So, for example, detectors that trigger shutdown typically need to be fast acting, and as do detectors that close dampers in ventilation systems. They also need to be fast acting. Another requirement could be the specific alarm levels or sensitivity settings of the detectors. So, for example, for gas detection, lower alarm levels typically provide a quicker response, but are more susceptible to false alarms if we do choose to use a lower set point. Other requirements include the size of the hazard we're trying to detect, so a cloud volume or a specific fire size that may cause that's of concern or that may cause escalation. Our coverage requirements, so that primarily drives the number and layout of our detectors. The intrinsic reliability of the system and its availability and maintainability. Any voting logic arrangements of systems that trigger automatic shutdown, typically that's initiated on 2 or more detectors. Any survivability requirements, and then crucially for, as I've said previously, for fire and gas detection, any interface requirements. So by that I mean it's the requirements on its interface in terms of the resultant action that comes out once we have detected a hazard. One further point I just want to say on the requirements is that they must have clear pass-fail criteria, so the performance can be sort of clearly assessed or tested. So for example, our response time, we may specifically require something that's less than 30 seconds, or our coverage target may be 80% coverage provided by 2 or more detectors. It's generally useful when we're assigning requirements on these systems to apply numbers, so then we can sort of clearly test whether these numerical targets have been achieved. So once we've got our requirements, we're in a position to choose an appropriate detection technology. So I'm not going to go into detail here on the different types of technology. I'd be here for forever. But as you know, there are many different types of technologies available, each with their own strengths and weaknesses. In addition, so the detector chosen must satisfy the requirements, but the requirements driven by the risk assessment, but also there are other factors such as the environmental factors or operational factors that must be considered. So, for example, in choosing an appropriate detector, we need to consider potential contaminants, so dust or sand, for example, the environmental conditions, so for example, is the structure you're attaching the detector to, does it have high vibration levels, or background noises, which is particularly pertinent to acoustic detection. Then of course there's the feasibility of installation of the particular detection in the area. So for example, open path gas detection may not be suitable for a congested environment. Then there's the maintenance burden. So for example, some detectors require more frequent calibration than others. And then there's many other factors, including the hazardous area certification. So for example, it must be appropriately certified for the area of operation. Otherwise, the detector itself then becomes a source of ignition for any flammable gas. So in parallel with detector selection, we must also choose a detector layout strategy. So this is actually crucial for a good fire and gas detection design. And a great reference that goes through different detector layout strategies is this CCPS reference called Continuous Monitoring for Hazardous Material Releases. So in this book, there are 5 different layout strategies proposed. There is a volumetric monitoring, which basically accepts the assertion that not all gas releases are going to be detected. And instead, this layout strategy focuses on providing a layout that prevents a damaging cloud size from developing into a cloud size that is a sufficient volume that perhaps could cause damaging explosion overpressure. So in this layout, our detector spacing throughout the volume is determined by the explosion risks in the area. And for this, we can either use a simple rule set approach. So for example, highly congested areas with a blockage ratio of greater than 0.3, for example. We may choose to place our detectors very closely together, and a commonly used approach is a spacing of 5 meters for highly congested volumes. And if we want to do a more accurate assessment, we may choose to do CFD based explosion studies, and this will give us our a more accurate damaging cloud size on which we would then go into the layout of our detectors, the spacing of our detectors. Another detection strategy is enclosure monitoring. This is quite simple, really. This is primarily aimed at detection for buildings, either the layout within the buildings or the external hazard to the buildings and the potential for ingress into the building. Another strategy that the book discusses is source monitoring. Now this is associated with detection of specific leak sources. So this method requires a bit more of an understanding of the nature of the release after loss of containment, and and therefore more sort of quantitative consequence modeling techniques are used for this type of layout. We also have target receptor monitoring, which basically means positioning of detectors in vulnerable or occupied areas. So this might be areas where people congregate or travel throughout a facility. And this type of layout strategy is particularly suited where there is a direct threat to personnel. So it is typically used for positioning of toxic detectors. And finally, we have perimeter monitoring, and this is achieved by placing detectors around the boundary of an area where there is potential for gas migration and into adjacent areas, into adjacent vulnerable areas where there could be, for example, escalation if it was if the adjacent area had non-EX rated equipment, or even sort of areas of public occupancy. So you can see that in tandem with choosing the right layout strategy, we must also choose the appropriate technology. So although the choose technology and define layout strategies are just shown as two discrete steps here, in fact they go very much hand in hand with each other. So for example, perimeter monitoring is best achieved using line of sight detectors, whereas source monitoring may actually be best achieved using acoustic detection. Volumetric fire monitoring may be achieved by using flame detection. However, the level of congestion in the area may mean that flame detection just isn't appropriate. There just isn't enough visibility in the area for the detector, and in which case we may choose to use heat detection. So that's just so you can see there just a couple of examples really on how those two middle steps, choose technology and define layout strategy, go very much hand in hand with each other. Okay, so now we have the detection requirements, the chosen detector technology, our layout strategy, and from that our detector positions ready. We can then go on to assess how the detection system is performing. So there are quite a few methods for assessing detector performance, and I'm actually only going to cover one here, fire and gas mapping. So fire and gas mapping is a technique that's used to assess detector coverage performance. Now there are two general definitions and approaches to assessing detector coverage. First one being here geographic mapping, where we determine the fraction of the area that's being monitored that is covered by the detection system. And then there is also scenario based mapping, where we look more at the releases and the fraction of releases that can be detected, considering the frequency and magnitude of these releases. So both of these methods have their strengths and weaknesses, and it can actually lead to quite some quite heated debate as to which of these two is the best technique. My view is that the best is it depends on the area in which we're assessing and the strategy chosen. It may be that the best technique is actually a combination of the two. So both methods have their strengths and weaknesses, and the concern with scenario-based mapping is that the resultant layout can end up being tailored specifically to the releases assessed, and therefore to ensure a valid layout we must assess many release cases, and this generally has to be undertaken by CFD, which adds to study expense. The more cases we have to assess, the more expensive our study becomes. And of course, we do have to choose a great amount of releases for scenario-based mapping to be effective, given what I said previously on in terms of the number of potential outcomes from a loss of containment situation. Geographic mapping, on the other hand, is less expensive, but it can lead to a larger number of detectors, particularly for onshore process facilities that cover much larger areas. So geographic mapping is best suited for monitoring where there is a significant explosion potential, where we're looking to ensure there's an appropriate density of detectors throughout a volume, a congested volume, for example. So in short, there is no right answer as to which is the best mapping technique, but the one chosen must satisfy the requirements and the layout strategy chosen. So at RISTech, we do primarily get involved at the fire and gas mapping stage of projects, but all too often we do so without a philosophy in place. I'm not sure why a lot of our studies we end up doing the mapping assessment without these preliminary steps performed. I don't know if it's the view that the fire and gas mapping will just simply provide the optimum solution, but this isn't true. Fire and gas mapping is only an assessment, only assesses the performance against the requirements, and therefore it must be, these initial steps must be undertaken before we get to the fire and gas mapping stage. So first we must define our strategy before going into the detailed analysis and number crunching activities. So finally, the final step is throughout the design process and commissioning and operations, the fire and gas detection system must be routinely reviewed. So these reviews may shed light on system weaknesses or poor performing system, in which case it may be necessary to initiate a management of change and reassess or redesign the system. So coming out of this review step, as I said previously, we may well end up going right back to the first step and reassessing our hazards. And if the fire and gas detection system has been identified as a safety and environmentally critical element, then an independent competent authority may be needed to come in and review the performance of the system and identify any recommendations for improvement. Okay, so just to summarise what I've discussed here is that fire and gas detection system design is very challenging, particularly for outside process areas where there is a lack of guidance and an almost too many options to the designer on how to solve the problem. And the variability of the hazard outcome as well, the number of potential outcomes for any single release scenario on a particular day, it varies greatly. And designing a system against these releases with the lack of guidance is a very challenging activity. So to counteract these challenges, it's very important that the project or facility has a fire and gas detection philosophy in place. So there is an agreed basis on which to design the system. Having this in place ultimately ensures the risks are reduced in an effective way as possible, and everyone can be confident that the fire and gas detection system has been well designed. And ultimately what we're aiming to do here by reviewing things, linking it to the hazard assessment and ensuring our requirements are tailored for the hazards at hand. Ultimately what we're trying to do is improve the safety at our facilities. Okay, thank you. Okay, that's it.
Thank you very much, John. That was very good, very interesting. We do have some questions from the floor. So in no particular order, well, starting at the top. Early on, Hans asked a question: why are 69% of the releases not detected? Common cause or material?
So that statistic comes from the offshore industry, and the main reason why a significant number of releases go undetected is mainly because of the layout chosen for the detection. So it may be that we just don't have enough point detectors located throughout the facility, or the layout might not be appropriate. So, for example, so taking a typical release scenario, a high pressure gas jet, for example, close to the release source, these releases have a very low cross section, and it's very easy for the detector just to shoot. Sorry, for the gas release just to sort of shoot past the detectors and go unnoticed. So for this reason, it's important to have, rather than just having detectors located close to the release source, it's important to have a sufficient number of detectors located throughout the volume. And this, I think the main sort of reason why 69% of the releases have been on detectors is primarily due to the number of detectors deployed in the area and the layout and the chosen layout.
Okay, great, thank you. Susan asks, hazard assessment technique is selected in relation to maturity of project. At what stage is fire and gas philosophy developed, typically?
So, really, fire and gas philosophy should be developed at the project start once. So, I mean, if we are undertaking other hazard studies or risk and hazard assessments, then the fire and gas philosophy may be undertaken after those activities have been completed or in tandem with those activities. But since the philosophy defines the overall objectives and requirements on the system, the earlier we start and agree the development of the philosophy, the better, really.
Great, thank you. And Susan also asks, is SIL rating applied to fire and gas? How would you differentiate requirements for facilities which could have catastrophic environmental impact, e.g. MOD, chemical warfare?
So SIL is applicable to fire and gas, but we've got to remember that SIL and SIL targets are typically assigned to measures that serve to prevent the hazard. But obviously we do need reliability targets on the system and on the detectors in order for it to be able to reliably provide the signal. So I mean, it just ties back really to the risk assessment. How, given all the measures we've got in place, how significant are the risks, and how reliable do we need the detection system to be? The thing is, with fire and gas detection as well, it's not just to do with the intrinsic reliability of the detectors and the system. We could have the most reliable system going, but if we do not position the detectors throughout the facility appropriately, then we still end up with a poor design. So the reliability, the intrinsic reliability of the detector and the layout go very much hand in hand, and they must be driven by the risks at the facility.
Great, thank you. And finally, John, just a couple of questions from Arturo. How early in the project execution phases we need to develop and design fire and gas systems? Do we need to have gas detection prior to issuing the P&ID for HAZOP?
Well, I mean, the fire and gas detectors aren't generally shown on the P&IDs. So for HAZOP purposes, I wouldn't say that the fire and gas design is required. However, you know, it's an activity that should be undertaken in parallel with that process. So as we are performing our hazard and risk assessment, we can then go on to, we should also be defining our detection requirements.
Yeah, Susan's said no HAZOP is for process design in the pipe, in my opinion. So
yeah, so the HAZOP is for when the material is within, exactly what Susan said. So when the material is within the process, whereas fire and gas detection is for when the material is out of the process and a loss of containment has occurred. So you know, that they are independent activities, but as part of the design process, you know, you would expect them to be undertaken in parallel with each other.
Okay, lovely. Thank you very much. If you wouldn't mind putting the last slide on, John. Thank you. Thank you very much, everybody, for attending, and I hope you found that very useful. As I said at the start, I look after RiskTech's training education business. So just to remind you, in case you haven't heard it before, we do have three main areas in which we deliver training. We've got an online MSc in Risk and Safety Management. We've got a lot of continuous professional development courses, also 100% online. And we do tailored and bespoke programs and courses for a range of clients across the world. That's the selling bit over. I do hope you enjoyed that. I hope you all have a safe and secure day. Thank you very much for your attendance.